Good morning, guys. So today I have a few things I want to cover with you. We're going to continue talking about limits just like we did last time. Hopefully you're feeling somewhat comfortable and hopefully you've put some time into the homework already. Today we're going to talk about continuity, and we're also going to talk about section 2.4, which is on the precise definition of a limit. And that 2.4 section is a tricky section. So let's get into it. I don't want to waste any time. Now, what I haven't done is really, well, the examples for the section here is going to be tricky. So let's just get into it. We'll figure our way through it. Okay, share. All right. So this is MAC2311.0H1. It's a lecture, and today is the 13th of January, 2021. Today we'll say a little more on section 2.3. We're going to discuss section 2.4. 2.3 is on limit laws and calculating limits. Specifically, there's one more theorem from 2.3 that I want to show you called the squeeze theorem. 2.4, remember, is on the precise definition of a limit. This is the tricky one. And then if there's time, we're going to talk about continuity. We'll introduce and work with continuity. Section 2.5. First, I'm okay with doing one more example from section 2.3. Are there any problems from the homework relating to the calculation of limits that you guys would like to look at? So I'd be happy to take a request from y'all. This class is small enough that I can ask, could I just get a thumbs up react if you have started homework 2? You guys know how to use the reactions in Zoom, right? There's a little button down there in the bottom on that black control panel that says reactions. Don't worry, I'm not going to judge you if you haven't. I just want to know what I should do and what I shouldn't do today. So give me a thumbs up react if you have started homework 2. Okay. That's all right. So I want to recommend strongly recommend that you do a little bit every day, right? Even if it's just solving one problem right after class, try real hard to do that. If you can't do it right after class because you got other shit going on, then towards the end of the day when you're eating your dinner, just solve one problem. I promise it will be a game changer. So let me grab a homework problem from the section from 2.3, and then we can get moving from there. So I think the stuff from the graphs we should all be getting pretty comfy with. There was a lot of that on the previous homework set. I'm not going to do one of those, but one of these that requires some clever algebra work I would like to look at. Be good, Henry. That's right, I moved that. What do you mean you're having trouble finding the damn site? Yeah, so we haven't gotten to limits at infinity. That's actually a topic I'm reserving for Friday. If you're already there, then you're in great shape. WebAssign timed out on me here. So I'm going to hold off on limits at infinity, Katie, for now. The first problem's up to problem 7 here. This is all just about plugging in the number, right? So we said last time polynomials and rational functions, you can calculate limits just by plugging in, by what we call direct substitution. And we proved that for polynomials and then deduced it for rational functions. I'd like to look at a problem something like 14, 15, 16. So I'll ask you guys, take a quick look at these. You can all see my screen share right now. Of 14, 15, and 16, what looks most intimidating? What would you most like a little guidance on? Okay, if I don't have a recommendation, I'm going to go ahead and make an executive decision here. Oh, you cannot see? It says it's sharing. Here, let's try again. Is that better? Can you guys see this now? All right, bueno. 14, 15, 16, what do we want to see? $15. All right, 15 looks good. That's what I was thinking too. Okay, so let's do it. I'm going to copy this down and then I'll tab back. Calculate the limit as h goes to 0 of quantity 4 plus h to the negative first power minus 4 to the negative first power all over h. Now, in a non-honors class, I would sit here for a minute and talk about order of operations, but we all know that the power here takes precedent over everything else. So the first step needs to be rewriting those powers as fractions so that we can get things working together. So this would be 1 over 4 plus h minus 1 over 4 all divided by h, and we need to think of these fractions as our grouping symbols. So of course, every numerator and denominator is thought of as being in parentheses. This is my first step. Now to actually start doing something with this, my goal, remember here, is to send h to 0. And the problem, of course, is this h in the denominator. I cannot send h to 0 as long as there isn't a factor of h in the denominator, because that would make the bottom 0. To get around that, I need to do some algebra here. And the algebra that's going to save the day in this case is just combining these two into a single fraction, right? Just clean up. We got this big mess of fractions within fractions. We need to clean it up. We're going to be brave. The trick to that, as we all learned in pre-calculus, is to have a common denominator between the two fractions that are being subtracted upstairs. This piece, the denominator is just 4. And in this piece, the denominator is 4 plus h. So I want them to have the same denominator. That means I need to give this guy a factor of 4, and I need to give this guy a factor of 4 plus h. So my next step, I always write my limit. I always write my equal signs. I've got my big fraction with h downstairs. 1 over 4 plus h is missing the factor of 4. So I will multiply him by 4 over 4. And 1/4 is missing the factor of 4 plus h. So I'll multiply him by 4 plus h over 4 plus h. And again, I'm thinking of this as all being in parens. The top and bottom of every fraction is always thought of as being in parentheses. Now the factors here in the denominator are 4 and 4 plus h. The factors here in the denominator are 4 and 4 plus h. These two little fractions upstairs now have the same denominator, which means I am now free to subtract their numerators. So I have lim h to 0. This piece is just 4 over 4 plus h times 4. And I'm going to subtract that, subtract this from that. So I'll have minus 1 times 4 plus h. And this is now my numerator. And it's all still being divided by h, right? So this is just how we subtract fractions. It just happens to be going on in the numerator of a big fraction. I can distribute this negative, I can distribute this minus 1 here. So I'll get lim h to 0. Again, being very disciplined about writing the limit, even if my hand gets sore. I have 4 minus 4 minus h divided by 4 plus h times 4, all divided by h. And I like these parentheses to remind myself what's the upstairs and what's the downstairs in the big fraction. Because otherwise you can get a little bit chewed up because division is not associative. The order does matter. 4 minus 4 is 0. So these guys eat each other up. And I am just left with negative h over 4 plus h times h, all over h, like so. I'll pause here for questions. Are there any questions about the algebra steps so far? Okay, then I'm going to partition the page so I can continue this in the blank space to the right. We're going to continue up here. My objective is to send h to 0. So I need to get rid of this h downstairs here. Here's a problem. Oh, sorry, this isn't an h here. This is a 4. This 4 is this 4. I drew it as an h. I'm sorry. My objective is to get rid of this h from the denominator. I have this fraction divided by h, and the trick here is that dividing by h is the same as multiplying by 1 over h. So again, just more work simplifying fractions. The numerator is negative h over parentheses 4 plus h times 4. That piece is this piece. And then instead of writing a big fraction bar and saying I'm dividing all that shit by h, I'm going to say, well, that's the same as multiplying all that shit by 1 over h. And now I can combine these as lim h to 0 negative h over 4 plus h times 4 times h, right? This 1 over h multiplies this fraction straight across. 1 times negative h is negative h. 4 plus h times 4 times h is that denominator. And now I am free to cancel the factor of h from the numerator with the factor of h from the denominator, and the result is lim h to 0. When I cancel these, the negative 1 from the top remains, and downstairs I have 4 plus h times 4. The miracle being that now the h is gone from the bottom. I have no more h downstairs. That h was this h, that h gets canceled, so now I'm free to send h to 0. As h goes to 0 in this apparatus, I get negative 1 over parentheses 4 plus 0 times 4. Well, 4 plus 0 is 4, so that denominator is just 4 times 4, so that's negative 1 over 16. And this is how it's done. So you got to remember your order of operations. You got to be real good with your algebra. The number one hindrance in calculus is algebra skills. Trig skills also, but algebra skills primarily. Questions on this? Okay. There's one more theorem from section 2.3 that we need to discuss, and that's called the squeeze theorem. In French, it's called the policeman's theorem. I have a lot of love for French mathematics, particularly Alexander Grothendieck. He's in your syllabus if you want to look him up. He called this theorem the policeman's theorem. But in America and elsewhere in the world, we call it the squeeze theorem. This says, if you have, so I want to take the limit of some function g of x. Right? I want to take the limit as x goes to a of g of x. But maybe g of x is badly behaved near a. Like the sine 1 over x, maybe it wobbles back and forth a lot. So this is a theorem to help us deal with that sort of stuff. It says if you have these three functions, f of x, which is no larger than g of x, which is itself no larger than h of x, for all x near a, and the limit as x goes to a of f of x is the same as the limit x goes to a of h of x, call it L, then the limit as x goes to a of g of x, our badly behaved function, must be equal to L also. Now in mathematics, we like to prove theorems. We talked about that last time, right? That is the main goal of mathematicians worldwide, is to prove statements like this. This is a true statement. And something that you use to prove a theorem, a little kind of mini theorem that's useful along the way, is called a lemma. So I have here for you a little lemma, and this is if f of x is less than or equal to g of x for all x near a, then the limits obey the same inequality. The limit as x approaches a of f of x is smaller than the limit as x approaches a of g of x. Proof of the lemma is going to be postponed. You can think of it as an exercise if you want, but it should be pretty intuitively appealing that if one function is smaller than another everywhere near the input a, then the limit of the first function should be smaller than the limit of the second function, right? If f is always smaller than g, then the limit of f can't possibly be larger than the limit of g. It's intuitively satisfying. Proof of the theorem. Suppose f of x is less than or equal to g of x is less than or equal to h of x, and take limits. By the lemma, I should take limits semicolon, by the lemma, the limits have to obey the same inequality. Now, if the limit of the outer functions the lim as x goes to a is equal to the limit as x goes to a of h of x is equal to L, then the preceding inequality becomes L is less than or equal to the limit as x goes to a of g of x is less than or equal to L. Right? So if f is less than g is less than h, then the limit of f is less than the limit of g is less than the limit of h. That's the lemma. Limits obey inequalities. If we include in our hypotheses that the limit of the outer functions is equal to L, then you can plug L in for this, and you can plug L in for this, which means that L is less than the limit of g of x, and that the limit of g of x is less than or equal to L. Suppose I told you that I don't know what my height is, but I know I'm no smaller than 6 feet tall and no larger than 6 feet tall. Can you deduce from that my height? Fuck yeah, you can. I gotta be 6 feet tall. The only way for some quantity to be both bigger than L and smaller than L, right, with a weak inequality, greater than or equal to, less than or equal to, is if the thing in the middle is actually equal to L. And that is the proof. That's what we wanted to prove. We wanted to prove that if the limits of the outer guys are both equal to L, then the limit of the middle guy is equal to L. So this is the proof of the squeeze theorem. What is this thing and how do we use it? Well, it's a tool for figuring out difficult limits of bounded functions whose behavior is not easy to deduce. I'm going to give you just a second to write down what I have here so that you can digest it. This is an honors class, so I want you guys to be thinking about theorems and their proofs. It will take time to digest. Don't expect for this to all sink in right away, but please write it down. Think about it hard now. Think about it hard later. In about 20 seconds, I'm going to show you an example. It's okay, Bubba. All right, example time. No, don't sign me out. Do we all remember the sine of 1 over x? That's this guy. Massively misbehaved near 0, right? Really, really hard to work with near 0 because it bounces back and forth infinitely often on any open interval containing 0. Bounces back and forth between -1 and 1. This is the sort of bad behavior that our theorem, the squeeze theorem, helps us get around. So let's look at an example. I'm going to tab back and forth between Desmos and the document camera, so don't panic if I tab away. Here's our example. I'd like to calculate the limit as x goes to 0 of x squared times the sine of 1 over x. The challenge here, focus. Limit laws don't help. Limit laws don't get the job done. Because if you tried to split this up as the limit x to 0, x squared sine 1 over x equals limit x to 0, x squared times limit x to 0 sine 1 over x. Remember what those limit laws said. There were some hypotheses built into the theorem that was our limit laws. It said, as long as the limit of f and the limit of g both exist, then the limit of f times g is the limit of f times the limit of g. Well, the limit of x squared as x goes to 0, this does exist. That's fine. That's 0. But this other guy is dne. That's the graph we were just looking at. And 0 times dne, who the fuck knows? Right? the limit law doesn't apply because this limit doesn't exist. That limit law that says the limit of f times g is the limit of f times the limit of g, the limit law we would use to rewrite that original problem like this, doesn't apply because this guy does not exist. So what we need to do instead is find a mathematical workaround. Now, normally we would say, let's try to do some algebra, right? Let's try to multiply by the conjugate, or let's try to factor the top and cancel with something that's causing problems downstairs. But there's no business like that that we can do. The sign of x is impenetrable. The sign of 1 over x is impenetrable. You cannot shove this x squared inside there. That shit is totally not kosher. You know that from trig. This box that's holding on to my 1 over x, that's holding on to my problem term, cannot be opened. So instead, we attack from the outside. Let me show you a graph. Back to Desmos. There's sine 1 over x. I'm going to label this as g of x, because it is the function that we're trying to work with. Here's the sine of or x squared times the sine of 1 over x. I'd like to adjust my axes a little bit if I can. Here we go. All right. This is the function I want to take the limit of, right? X squared times the sine of 1 over x. I'd like to take the limit as x goes to 0. Looking at this picture, we see a handful of interesting things. First, we do have this rapid oscillation. This thing is bouncing back and forth quite a lot as we come in towards 0. And zooming in doesn't help. It's still just like this wave just gets wavier and wavier. That's coming from the sine of 1 over x, right? As the inside gets bigger and bigger, the frequency increases. The oscillations get faster. But looking at the graph, it looks like the thing is going to 0. It's going to 0 in a really weird way with all this wobbly shit, but it does appear to get closer and closer to 0 as we go closer and closer to 0 in our x values. The tool for this is the squeeze theorem. Let me introduce the functions f and h. Shut up. F of x and h of x. I'm going to call h of x, x squared. I'll change its color here to green. Notice that my function g is bounded above by h. The red function is always smaller than the green function. And similarly, if I let f of x be negative x squared, the red function is bounded below by the blue function. My function is always bigger than negative x squared and always smaller than positive x squared. That is precisely the setup for the squeeze theorem. My function g of x is bounded above by some well-behaved function and bounded below by some well-behaved function. Now, the squeeze theorem says is if both of those outer functions have the same limit, then the middle guy has that limit also. The reason this is called the policeman theorem in France, BT dubs, imagine you are g of x, f of x is a policeman walking behind you along the street, and h of x is a policeman walking in front of you along the street. This says if there's a policeman behind you and a policeman in front of you, and they're both going to the jail, then your ass is also going to the jail. So how do I use it here? The way we make use of the squeeze theorem, right? This note is relevant, but it just tells us what we can't do. It doesn't tell us what we can do. The way we make use of this is by setting up an inequality, right? This statement is all about inequalities. It starts with an inequality like this. So I'm going to think of this as my function g of x. And my goal is to build an inequality with my function in the middle. You need to begin with an observation. And to help with that observation, I'm going to come back to Desmos. and look just at y equals sine 1 over x. All right, as badly behaved as this function is, do you notice any boundaries? What's the largest this function ever gets? Anybody? Oh, sorry, let me look in the chat. I apologize. Yeah, the largest this function ever gets is 1. And the smallest this function ever gets is -1. And that's true for any sine function. I don't care what you put inside the sine function. Because the sine function is defined according to the unit circle, its y values along the unit circle never goes above 1, never goes below -1. So no matter what you have inside the sine function, it's always bounded between -1 and 1. So our observation is that -1 is less than or equal to the sine of 1 over x, and that the sine of 1 over x is less than or equal to 1. You can write it in a compound inequality like this. This is our starting point. From this inequality, which we know to be true by virtues of geometry, we can build an inequality involving the function x squared times the sine of 1 over x. Recall that you can multiply through an inequality by any non-negative quantity without messing up the inequality, right? So I could multiply everything here by 5. I could multiply everything here by 10. I could multiply everything here by e to the x if I wanted to. But my goal is to make this function show up in the middle. So by what non-negative quantity should I multiply through this inequality? Anybody? What can I multiply through this inequality by in order to make my function x squared times sine of 1 over x show up in the middle? Yeah, x squared. X squared is non-negative. So it's safe to multiply through an inequality by it. And doing so will make my function show up in the middle. So the result is -x squared is less than or equal to x squared times the sine of 1 over x is less than or equal to positive x squared. And now I want to remind you of the picture we were playing with over here. My function, -x squared, positive x squared. Let's zoom way to fuck in on this. There we go. All right. So this picture is expressed algebraically in this inequality. Now, if the limit of the function on the left at 0 is equal to the limit of the function on the right at 0, then the limit of the function in the middle at 0 must be that shared value. Policeman behind you, policeman in front of you. If they're both going to the same place, then you are going to that place. So now, lim x to 0 of -x squared. What is that? As x goes to 0, what does as x goes to 0, what does -x squared do? Well, -x squared is a polynomial, remember? So you can calculate this limit just by plugging in. What is this limit?
It goes to 0 as well.
Good, it goes to 0. And the limit as x goes to 0 of my upper bound function, x squared, this is also 0. I should get rid of the so here. I was saying now this and this. So by the squeeze theorem, the limit as x approaches 0 of x squared times the sine of 1 over x, this is 0 also. That's the squeeze theorem, and that's how we use it. So if you're trying to calculate a limit that is, for whatever reason, very difficult, you can employ the squeeze theorem by building an inequality with your difficult function in the middle. Then check and see if the limit of the bounding functions match. Since in this case they do, the function that bounds my function by below goes to 0, and the function that bounds my function from above goes to 0, it must follow that my function goes to 0 as well. Right? This is the squeeze theorem, and it's an incredibly useful tool. It's useful in Calc 1 in some places. It's real useful in Calc 2. We're going to use the shit out of this in Calc 2. So play with it, get comfy with it. I think I put 2 or 3 problems in your homework set that have to do with the squeeze theorem. Questions on this example? Okay, let's see how I'm doing on time. 11:38. We go to 12:15, right? Okay. The next thing we're going to talk about is the precise definition of a limit, section 2.4. I'm going to introduce this here, and I still, like I said, I haven't added any problems to your homework set. These are really proof problems. They're not problems that are super easy to like point and click web assignment bullshit. But I want to show you this thing and see if you can kind of understand it, and we'll slowly, you know, I'll give you a couple problems on it, maybe in this week's homework set, maybe in next week's. I'm going to use some religious terminology here because it's just the easiest way to describe what's going on. Please don't be offended if you have any particular religious beliefs. I promise it's not my intent to offend. So first, let me show you the definition. Here's what it actually means when we say the limit of a function at a is this number. We say that the limit as x approaches a of f of x is equal to L, provided for every positive number epsilon, for every epsilon greater than 0, there exists a positive number delta. These are lowercase Greek letters, epsilon and delta. So we say the limit x to a, f of x equals L. This is a true statement, provided for every positive number epsilon, one can find, or there exists, a positive number delta, such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta. This is going to take a little bit of time to explain. So hold on to your pants, get this written down first, and then just think along with me. You may remember that the absolute value of f of x minus L is the distance from f of x to L. And the absolute value of x minus a is the distance from x to a. So what we're saying here is that if God hands you some positive number epsilon, you can find a positive number delta such that if x is within delta of a, that is the distance from x to a is smaller than delta, that guarantees f of x will be within epsilon of L. All right, another way of writing this last statement here is that this implies this. So if you want to prove that a certain limit exists, right? The limit as x goes to 0 of x squared is 0, for example. You have to pretend that God hands you some number epsilon over which you have no fucking control. Then come up with a number delta, depending on epsilon, such that if x is within delta of 0, then x squared is within epsilon of 0. There's a picture. Let me draw for you this picture. All right. Let me draw it like this. I'll say here is A. And you can imagine that this is a hole or that this is filled in. Just for shits and giggles, let's imagine it's a hole. If I looked at this picture, then I think we would all agree that the limit of this function f of x as x approaches a is the number L. Yes? Because if I get closer and closer along this graph to having x value a from either side, my y values do get closer and closer to L. The way you understand that in the context of this formal definition is to say that, again, God hands you epsilon. You have no control over epsilon. This upper bound here is L plus epsilon. This lower bound here is L minus epsilon. You have to find the number delta such that if x is in this delta interval about a, f of x is guaranteed to be within the epsilon window of L. And this is weird because we're used to thinking of this getting closer and closer to a and tracking what the y values do. This kind of goes the other way. You have to imagine this window shrinking down and being able to find this window as a function of the shrinking here. It's not a simple thing, but it makes sense if you think about it very carefully. If I say I want f of x to be within 0.01 of L, you have to find me a delta that will guarantee f of x is within 0.01 of L as long as x is within delta of a. Again, not a simple thing, but if you spend time thinking about it, you will be able to make sense of it. There are some really good books. I know many graduate students who struggle with this stuff, so expect to take some time here. I'm going to work a very, very simple example for you. All right, I'll work one or two simple examples for you here. The limit we used, do we need time to write this down? So the idea is that given an epsilon window, you can find a delta window such that if you take any x value from this delta window, the y value will be in the epsilon window. That's the idea. And then you imagine the epsilon window shrinking, the delta window shrinks with it. As long as for every epsilon window you can find a delta window, then we say the limit exists. It's a complicated statement. All right, simple example first. Prove that the limit as x approaches 0 of x is 0. So here, L is 0 and A is 0. Every proof and analysis starts off the following way. Let epsilon greater than 0 be given. All right, that's actually a joke in analysis. Let epsilon be greater than 0. It's always there. Let epsilon be greater than 0. We need to find delta such that if absolute value of x minus 0 is less than delta, then the absolute value of f of x here, which is also x, minus 0 is less than epsilon. So here f of x is x, right? Now in this case, it's easy because these inequalities are the same thing. Take or pick delta equal to epsilon. Then, if the absolute value of x minus 0 is less than delta, it is true that the absolute value of, let me replace this by f of x. Yeah. Then it is true that the absolute value of f of x minus 0 is less than epsilon, because the absolute value of f of x minus 0 is just x minus 0. In other words, take delta equal to epsilon. Then, if the absolute value of x minus 0 is less than delta, the absolute value of x minus 0 is less than epsilon, because the absolute value of x minus 0 is the same as the absolute value of f of x minus 0. All right? It's less than delta, which is equal to epsilon. This work with absolute value inequalities only gets harder. I think maybe this example is so simple that it's hard to see the mechanics. So I'll let you write this down, and then I'll show you a slightly more complicated example. All right, that's the proof. Another example. Prove that the limit as x approaches, let's say, 2 of the function 5x is equal to 10. This is a true statement. 5x is polynomial. We know from our theorems that you can evaluate polynomial limits by plugging in 5 times 2 is 10. But I want to show you this in the delta epsilon setting because it's much harder to work with. Here, of course, f of x is 5x, a is 2, and L, our suspected limit, is 10. We need to show, so proof. We aim to show that for every epsilon greater than 0, that's what I mean by God hands you, right? Like you don't get to pick epsilon. Epsilon is an arbitrary positive number. We aim to show that for every epsilon greater than 0, there is a number delta greater than 0 such that absolute value of x minus 2 being less than delta implies the absolute value of f of x minus 10 is less than epsilon. And in general, your number delta is going to be a function of the arbitrary positive number epsilon. You can assume epsilon is constant, but you cannot assume anything besides epsilon being a positive constant. So this is what we want to show. We aim to show that given any positive number epsilon, we can find a number delta such that if x minus 2 has absolute value less than delta, then f of x minus 10 will have absolute value less than epsilon. The normal way to do this, that last example was a little too simple maybe. The normal way to do this is to take your inequality involving epsilon and blow it apart algebraically. Work with that until you get an inequality involving x. So here we go. Now, absolute value of f of x minus 10 is less than epsilon. Well, what is f of x? F of x is 5x. So that's the same as saying the absolute value of 5x minus 10 is less than epsilon. You can factor out a 5. That's the same as saying 5 times the absolute value of 5 times x minus 2 is less than epsilon. Now, absolute values play nice with multiplication. Side note, absolute value of a times b is always the absolute value of a times the absolute value of b. So the absolute value of 5 times x minus 2 is 5, the absolute value of 5, times the absolute value of x minus 2. So, remember what my goal is. My goal is to find a number delta such that if x minus 2 has absolute value less than delta, I'm guaranteed f of x minus 10 has absolute value less than epsilon. The absolute value of f of x minus 10 being less than epsilon is the same thing as saying absolute value of 5x minus 10 is less than epsilon, because f of x is 5x. Factor the 5, pull the 5 out the absolute value, and what do you get? Well, let me divide that 5 over, and I get absolute value of x minus 2 is less than epsilon over 5. So, if the absolute value of x minus 2 is smaller than epsilon over 5, these are if and only ifs. These are logical equivalencies. If the absolute value of x minus 2 is less than epsilon over 5, then it is true. You can read this backwards. Then it is true that the absolute value of f of x minus 10 will be less than epsilon. So delta equals epsilon over 5 works because if abs x minus 2 is less than epsilon over 5, then 5 times abs x minus 2 is less than epsilon, which is the same as saying, right, I'm just reading this shit backwards now, is the same as saying absolute value of 5 times x minus 2 is less than epsilon, which is the same as saying 5x minus 10 has absolute value less than epsilon. And this literally is absolute value of f of x minus 10 is less than epsilon. So if delta is equal to epsilon over 5, then for any epsilon in the universe, as long as x minus 2 has absolute value less than delta, chosen as epsilon over 5, then it's true that f of x minus 10 will have absolute value less than epsilon. That's the game. This, lads and ladies, is called real analysis. This is it. All right, this is what I do for a living. This is what I did in grad school. This is the good shit. It takes a while to get used to. Paul Halmosh, one of my favorite mathematical writers, wrote a brilliant book called I Want to Be a Mathematician. And in that book, he talks about how much he struggled with this. It's called epsilonic analysis. It's not easy. These are sort of the easiest examples one can conjure. Before I show you harder examples, which I will do down the line, I want to show you the picture that comes along with this so you can start to try to develop the intuition. First, questions on the actual manipulations here. Let's save questions on the logic for a second. Questions on what we literally did with these inequalities, any of the steps. Okay, now questions on the logic. Really, everything on the second page is superfluous. You don't actually need this. This is everything. This shows that if the absolute value of x minus 2 is less than epsilon over 5, then the absolute value of f of x minus 10 will be less than epsilon. The proof is all right here. All right, really like right here and here. I'm going to draw for you the picture now. This is the graph of f of x equals 5x. Actually, let me draw this with slightly more realistic slope, because the slope is kind of important here. All right, we'll say this is a line with slope 5. So here's 1, 5. Here is 2, 10. And what we showed is that if you have a little epsilon window about 10, so this would be 10 plus epsilon, this would be 10 minus epsilon, then in order to guarantee that we are within that epsilon window, it suffices to be within a window 1/5 the size. So this right here, this x value, would be 2 minus epsilon over 5. And this right here would be 2 plus epsilon over 5. And those epsilon over 5s, those are the delta. So delta equals 3. Epsilon over 5 works in the definition. And the idea here is that epsilon is an arbitrary positive number over which we have no control. You can imagine God giving you smaller and smaller and smaller and smaller epsilons. As long as you always have delta equal to epsilon over 5, this window will shrink down along with this window. And that's what it means to say that that limit exists and is 10. So this is the picture for the problem we just solved. I want to give you time to digest this. I don't want to overwhelm you. So rather than showing you a more complicated example with this, the next one we're going to do is x squared. We're going to show that the limit as x goes to 0 of x squared really is 0. It's going to involve more direct work with the inequalities. I want you to take the time and really, really understand this. Now, how am I doing on time? Our class goes from 11 to 12:15, right? So let me take these last few minutes and show you a little bit of continuity stuff. Last call for questions on the delta epsilon thing that we did here. These are a little bit harder to find good resources for. The textbook's treatment of this shit is weak. All right, it's not very good, but it is here. The way they address it, you know, they make it look scarier than it is by plugging in a bunch of specific numbers for epsilon, but here's the picture, right? Here's the same picture we have. I don't know what function they're using. They're doing something slightly different. But if the idea is we want to make sure that whenever x is in here, f of x will be in here. And you don't have any control over epsilon. So you have to control using delta. God gives you epsilon. And to make sure that f of x lives in this epsilon window about 5, you have to come up with a delta that guarantees as long as you're within delta of 3, the output, the blue, will be within epsilon of 5. The way it always shakes out is that delta ends up depending on epsilon. If you read this, you will have a little bit of help on how to handle these inequalities. I will be working more with these inequalities on Friday as an extra example, but I encourage you guys to read.
You are muted now.
All right, thank you guys. Sorry, Zoom just crashed. I have no idea why. If you want a better treatment of the delta epsilon stuff than what you find in your textbook, I am going to link you to a very valuable text here. This is a book by Rudin, Walter Rudin, called Principles of Mathematical Analysis. Don't tell anybody where you got it. All right, you got it from me, but don't tell anybody where you got it. This book has a very careful treatment of limits, lots of good examples. It's hard to read though, okay? I invite you to read the textbook section 2.4. I invite you to look at Rudin there. That's baby Rudin. It's the easier one, but it's still quite hard. I'll tell you that I'm not going to beat you to death with the delta epsilon stuff, but I am going to give you a little bit of homework on it, and there may be 1 or 2 concept-focused questions on your first exam relating to it. I'll come back to that once you've had a little bit of time to digest, and we'll prove 1 or 2 more limits that way in class on Friday. But the last thing I want to talk about today is continuity, which is section 2.5. We talked a little bit about this last time. I gave you the definition, right? We say f of x is continuous at x equals a, provided the limit as x approaches a of f of x is equal to f of a. And real quick, you can imagine that because the limit here is defined in terms of delta epsilon stuff, there is a whole different definition in terms of deltas and epsilons for continuity. And the same is true for derivatives, and the same will be true for everything in calculus. It's all built on deltas and epsilons. But we're going to come back out to the slightly easier space where we work just with the lim notation. We talked about the ways this can fail last time, right? We said this limit might not exist. This function value might not exist, or both of them can exist, but maybe they're not equal to each other. Now, I want to go a little bit further in this definition today and say, we say that f of x.
Oh, we can't see the screen.
You serious? God damn it. Zoom's fucking us up. All right, here we go. I'm so sorry. So here's the definition of continuity we introduced last time. Should already be in your notes. I'm going to take this a little bit further just to teach you some vocabulary now. We say f of x is continuous on the interval I. So I can be any interval if f of x is continuous at each number a in the interval I. And then finally, we say f of x is continuous full stop, like just straight up f of x is continuous if f of x is continuous at every number a in its domain. Right? So a continuous function is one, is something, continuity is something that happens one point at a time, right? You can look and say, is this function continuous at 2? Is this function continuous at 0? Is this function continuous at 5? And every time you want to check something like that, you have to check that the limit as x goes to 2, say, of f of x is equal to f of 2. Is the function value equal to the limit? That can fail in any of the three ways we discussed previously. If I want to say a function is continuous on the interval 0 to 1, that means that this definition is satisfied for every single number in the interval 0 to 1. And you can replace the interval 0 to 1 with your favorite interval I, and that statement is still what we mean by that. And then finally, we say a function is continuous, period, like is just a continuous function, if it's continuous at every number in its domain, right? Every number a in its domain. A is the place we're talking about continuity being in question here. There's a good problem on this in your homework that I want to discuss really quick. So answer the question, is the function f of x defined piecewise as, what was it? X squared minus 3x over x squared minus 9 for all x different from 3, and 1 if x is equal to 3, continuous at x equals 3, question mark. So if yes, why? If no, why not? The thing we need to check is the limit as x approaches 3 of f of x equal to f of 3. So we're going to calculate this limit, we're going to calculate this function value, and we're going to see if they're equal. If the limit doesn't exist, the function's not continuous at 3. If the function value doesn't exist, then the function's not continuous at 3. And if they both exist but happen to not be equal, then the function is not continuous at 3. Let's start here. What is f of 3? Does this number exist? Is 3 in the domain of f of x? And if so, what is the function value f of 3? I see something in chat. Let's see here. Oh, damn it, open up. Very good. Haley's got it. F of 3 is equal to 1. By the definition of the function f. Right? F of x is defined piecewise. It says f of x is equal to this rational function if x is not equal to 3, and it's equal to 1 if x is equal to 3. All right, so f of 3 is 1. What about the limit as x approaches 3 of f of x? Well, that would be the limit as x approaches 3. Remember, we don't care about what happens at 3 for the limit. We care about what happens nearby. Well, that means we're considering x's which are different from 3, not x's that are equal to 3. So we're going to use this piece. So that's x squared minus 3x over x squared minus 9. And you notice that if you try to plug 3 into this expression to calculate that limit, the top and the bottom, they're both 0. So in order to calculate that limit, we have to use the same sort of tricks we used at the start of class today and in class last time. We need to do some algebra. Let's factor this top and bottom and see what we get. The top factors as x times x minus 3. And the bottom factors as x minus 3 times x plus 3. And as long as x is not exactly equal to 3, I'm allowed to cancel these sum bitches. And again, the limit doesn't care about the value at 3, it cares about the value nearby. So for the purposes of the limit, this is fine. What's left upstairs is an x. What's left downstairs is an x plus 3. Now this function right here, x over x plus 3, he doesn't have any problems at 3. So I can evaluate that limit directly by plugging in. What is this limit? Well, if I plug in 3, I get 3 over 3 plus 3, which is 3 over 6. Yeah, good, Haley, which is 1/2. So is the function continuous at 3? No, it's not. Because the limit as x approaches 3 is not the same as f of 3. So what we have here is a function that's discontinuous at 3. I think it would be good practice, and this is where I'll leave you guys for today because we are exactly out of time. Good practice would be for you guys to try and graph this function. Graph this and see what the discontinuity at 3 looks like. This function actually has 2 discontinuities. It's discontinuous at 3 because of the way it's piecewise defined at 3. The other discontinuity is at -3 because that's the other place this denominator blows up. That's the other place this denominator is 0. So there's 2 discontinuities here. And I would like you guys to graph this function. Describe the discontinuity, and doing that will help you with the homework problem. I think this is like number 29 in your current homework set. All right. Next time, we're going to talk a little bit more about section 2.4 and the precise definition of a limit. I'm going to work a couple harder examples. So I implore you guys to read section 2.4 in the textbook. Look at the example I did here in class, Google, look at YouTube videos, whatever you think would be helpful. That book from Rudin is excellent. It's a very good book, but it's very hard to read. So if you want to go down that rabbit hole, you're welcome to do so. I'd be happy to talk about in office hours with you, but I won't be spending class time on Rudin. That is it. Next time, again, limits at infinity and a little bit more of this precise definition of limit and continuity stuff. Hope you guys have a lovely rest of your day. If you do need to see me, I have an office hour this afternoon. Don't hesitate to come by that. Otherwise, I will see you on Friday. All right. Any last minute things before we go? Okay, then I'm gonna go ahead and sign out in the meeting. I hope you guys have a good rest of your day. Again, if you need to contact me, come by an office hour or send me a Canvas message. Take care, guys.